here's what, hopefully I steal this idea from Kevin. By the end of today's session, hopefully we will learn high level understanding of different types of sensitivity analysis and know how to perform this type of sensitivity analysis using RMS, and know how to choose the best type of sensitivity analysis for your application, and know how to perform multi-phase simulation with RMS. So just like a high level thing for model construction and refinement. First, you can build a model using RMG, which we already learned to do yesterday. You start with initial species and some initial concentration, temperature, pressure, and the potential, if in the future, hopefully good for that. And in the second step, as you did yesterday, in one of the lecture, you ran a notebook to do simulation, RP analysis, and flux diagram plotting. And that's done through the Python graph version of RMS. And usually after you do all this, you want to check whether the model makes sense. If yes, congratulations, you have a complete model. Rarely go that way. More often, you will find no. You'll find that some parameters didn't look right, and you will want to do some parameter refinement, and where we just learned how to do that with ARC. And in the morning, Kevin gave a really detailed talk on how to add these new data to RMG, and hopefully you would do this iteration for many, many times until it converges to something that you're proud to present. There's slightly chance that it could be something that you need to improve on your RMG settings, and we will learn more about this in the lecture tomorrow. But today we're going to focus on the second step, which is some simulation and sensitivity analysis using RMS. So there are two parts of model analysis that people often use. The first is to know what pathways are running. And this we already learned how to do yesterday using flux diagram or RP analysis. You can know what important reactions are running. And we also learned how to check what has changed since the last iteration of model. And using this and with your chemical knowledge, we should really ask ourselves, do the pathways make sense? Are there expected pathways that are missing? And a lot of times when this happens, it's because some parameters in the model are not good. And how do we identify those parameters that are not good enough? People usually use sensitivity analysis. And before I jump into sensitivity analysis, let's look at some high-level size and characteristics of the chemical system that we're interested in. So usually it's an ODE system. The whole equation can be presented as the middle one. There will be a quite different size. There are tens to thousands of species, or tens and thousands to hundred thousands of reactions. And the U over here are the most of species plus temperature, pressure, volume, or other thing that we solve for at the same time. And the length of this would usually be similar to the number of species in your model. And the parameter here is the Gibbs free energy of species and Gibbs free energy of formation of species and rate coefficients of reactions. So the length of parameter is number of species and number of reactions. So for sensitivity analysis, oftentimes we want to know how much the change in a parameter make a difference on our outputs. And we also want to know what parameters affect our solution the most. So there are just some clarification. The sensitivity value is often a function of three things: what species the sensitivity is for, what parameter is for, and at what time points. So you usually would say, for example, hydrogen is sensitive to the rate coefficient of this reaction at this time. You wouldn't say that, oh, hydrogen is sensitive or this reaction is sensitive. That doesn't quite make sense. Okay. So usually we're only interested in the sensitivity of some species. We don't care about the sensitivity of all species. Because some species is usually related to a model. Say if you're doing a pyrolysis or combustion, usually you care about the sensitivity of your fuel species, or those like key species that we can observe during experiments. So because of this, we usually care for the sensitivity value of this small number of species against all parameters. So you want to know how much the prediction of the concentration of this species would change if you change the bit free energy of formation and rate coefficients of all the possible things at some certain time. And the parameters, so what parameters that we want to refine or to do calculations or do experiments from? It's usually parameters that the interested species is most sensitive to at the interesting time points. What I mean by that is it depends on the experiments that you perform. Say you have a ignition delay type of experiments, you might want to look at the sensitivities right before the ignition time. Because that will affect your ignition delay time the most. And for experiments that you just like do a sample and then you measure the concentration using like GC or anything like that, you might be interested in the sensitivity at those sample time. So once you have the sensitivity analysis information, you should recheck the parameter sources. These are all possible parameter sources in RMG. It could be RMG estimates from group trees. And in this case, you want to refine those parameters. It could be from RMG libraries. And the libraries can have many different sources, like experimental measurement, quantum chemical calculations, or for those cases, you should really check what type of experiments they are, what are the error bars. For calculations, you should check their level of theory and whether they apply any sort of corrections to it to improve their accuracy. And if it's from empirical estimates, you want to refine those parameters as well. Now we're going to talk about different ways to do sensitivity analysis. The first one is quite commonly used, but not necessarily the best. Go brute force local sensitivity analysis. It's usually you just apply a small perturbation to your parameter and you simulate it many times, and you use those values to calculate the sensitivity difference. And you can use, backward difference, central difference, and all that. The good thing about it is that it's quite straightforward. You just run the same thing multiple times with some perturbation to your parameter. But the bad thing is that it's not numerical accurate, and you kind of need a priori knowledge on what is a good perturbation to your parameter. And as I stressed before, we're usually interested in this value, the sensitivity of certain species to all parameters, which means that if you want to know this value, the sensitivity for certain species, you need to perturb all the possible combinations of parameters to get this. So it doesn't scale quite well. And here I'm going to talk about types of sensitivity analysis tools that try to do this problem in a more easy and clever way to give you sensitivity value faster. And these tools are the sensitivity analysis I'm going to mention here are all available in RMS, which we'll do together in the notebook. So here are 4 types of sensitivity analysis, and I'm going to talk about them first, and then we will run the notebook together. The first is traditional forward sensitivity analysis. Basically, it's differentiating the U to parameter in time to get this equation, and I refer to this as forward sensitivity equations. It's called forward sensitivities because you also integrate this sensitivity equation forward in time. And there will be a version later where we'll do something backward in time, so they will kind of just make the difference there. And the good thing about this, you get a sensitivity of this species that you care, of all the species that you care about for some parameter at all time points. But the bad thing is that you can only get this, which is the dependency on all the outputs on one certain parameter for each equation. And you need to stop the whole system in order to get the actual sensitivity that we care about, which is the sensitivity of one species to all parameters, because of the nature of how this equation is constructed. If you look at it here, it solves for the sensitive, like the sensitivity of all outputs on one parameter, but what we want is sensitivity of one output to all parameters. It's quite key here, important here, because in this case, say you have a big system of 100 species. I only care about sensitivity of one species. You are forced to solve 100 species sensitivity in order to get a one. So you kind of waste some time there. So because of this, here one way to speed this up, which is use multi-threading. Essentially, it tries to solve this equation in parallel. So you get some speed up over there. You can speed up for each parameters here. So you can speed up for one equation, the equation size is number of species, but for all the parameters, you can solve in parallel. The good thing is you still get the sensitivity at all time points and you get parallelization speed up, but you still need to solve the full system, like the sensitivity of all species in order to get that sensitivity of one species that you care. So it really makes you wonder, can we just solve for that directly, like sensitivity of one species? The problem is that we cannot really separate out the dependency on all outputs using the same way we formulate for sensitivity. Like if you try to do the math over here, you'll find that this term doesn't separate out easily so that you can get an easy ODE system to solve that sensitivity equation. Instead, there is a already well-formulated way to do this, which is to solve for adjoint sensitivity. So the difference here is that I'm not gonna go into the math details. If you're interested in the derivation of adjoint sensitivity, there are many well-documented notes, like by Professor Steve Johnson, kind of one of the legends in our NMT. You can check out those math. But basically, if we formulate a system in a way such that you can solve for a much smaller system to get that one sensitivity directly without solving for all sensitivity. And so the good thing about it is that it scales really well. You can get that sensitivity of one species directly against all parameters. And you can also get parallelization speed up. So how it works is that instead of solving in forward time, it somehow formed these adjoint equations where you would solve it in backward time. And it used some clever mathematical tricks to separate out the dependencies. That's kind of the high level understanding of it, but please definitely check out these notes to know how exactly they do that. And using this, you don't need to solve for a gigantic number of equations just to get one sensitivity that you care. You can just solve for that one small equation, not necessarily small. But the number of equations you solve is smaller and you get speed improvements from that. And this is important because a lot of times when you do model improvements, you only care about like the prediction of some species and you want to just get that directly. So there's 4 things that we support in RMS is transitory sensitivity analysis. Instead of solving the ODE system, it kind of approximates the solution of sensitivity using trapezoid rule. So instead of solving the sensitivity matrix, it kind of get this like not numerical, semi-analytical equation here, and then you instead of solving the sensitivity, you kind of solve a sensitivity average over time. And this is really good because you don't solve any ODE equations here. It's pretty expensive to solve for any ODE equations. It's just a direct computation, direct pluses and multiplication and explanation, really fast. And the good thing is fast. It's really good to use for quick evaluation when you're just trying to build a model. The bad thing is that it's not numerical accurate, but we will show that it shows the same ranking as a traditional numerical accurate result. So I applied this sensitivity on the super minimal example. You can see that all these 3 versions I present, the traditional 4 sensitivity, threaded 4 sensitivity, and adjoint sensitivity, they are all numerically accurate, so they all give the same result. For transitory sensitivity, it kind of gives you the similar ranking and similar shape, but the values are not right. But this is useful enough when we try to build models, because now you can know, oh, these are the reactions that I should calculate for, right? Like without spending a ton of time solving for sensitivity equations. And it's the similar result for thermal. So a final high-level comparison, I personally think that you should never use brute force sensitivity analysis. This is because it's not numerical accurate. And if you can accept not numerical accurate, you should use transitory sensitivity, because to solve for brute force, you spend this amount of time. But for transitory sensitivity, you get it instant. Like if you can suffer from the numerical accuracy part, choose the faster one. But if you want numerical accuracy, you should choose either from this or this, threaded forward or adjoint sensitivity. And this is because if you need the sensitivity for all species, which is quite rare when building a model, or if you need sensitivity at all time points, which is also quite rare when you build a model. So a lot of time I would prioritize using adjoint sensitivity to get the sensitivities for some certain target species to improve your model. And I made a simple map to know, do you need numerical accuracy? If you don't, use transitory. If you need it, do you need sensitivity at all time points and for all species? If you don't, you can use adjoint. And if you do, which is quite rare, you can use threaded forward sensitivity. And this is how kind of it plays into the diagram of building a model. When you're just doing this iteration to improve the model, you can use transitory sensitivity, which give you approximation of sensitivity, from which you can know what parameters you should improve in a very fast, like it's instant. Until we get a complete model, you can do a slightly numerical accurate version for your final paper you want to publish, so it's pretty. So with this, we're gonna run this, a few warnings. The rate constant can actually appear, there are only some kind of rate constants that can appear in sensitivity analysis. Sometimes when rates are so fast that they are not limiting anything. So even when there's some error in those rates, it won't show up on sensitivity. And sometimes they are so slow that they don't form anything. There's no flux, so they don't affect the branching, so they don't show up on sensitivity. So strictly speaking, the rate coefficients are only sensitive in the in-between region, but probably instead the uncertainties in the parameters can often large enough that across the whole space. So the takeaway point is that even if some reactions don't show up in your sensitivity analysis, it can still be important, but it's just that the parameter is so wrong in your current model, it won't show up. Those are the hard things to debug for. I personally don't have a magic trick to tell you how to do that, but another warning is that it will miss those. And another thing is that the sensitivity analysis will only tell you what is important, but it will not tell you why is important, and why is often important. Okay, that's kind of mouthful. The why is actually a crucial thing to know. And you usually you can know the why from like our field flux. So you know like these pathways are running, and it might be why that's causing this things are important and sensitive. So here is to just say that don't completely count on sensitivity analysis. You want to combine with other tools that we presented to you yesterday. And with this theory part, now let's perform the sensitivity analysis together. Here's the thing that you can type in and try. So first you download those files and you put it into the RMG shared folder. My RMG files folder as yesterday, that I think we all do. If you already active your RMG container, you can reconnect using that, but I assume that you still have it connected.
So For a lot of you, you can probably hold control and then just left click on that bottom URL and it should just directly take you in. If that doesn't work though, follow the copy paste and like typing in the location as is on the screen.
Yeah, I think this, let's go to the my RMG files folder instead, not go to the default one, because the new notebooks that I send out would, when you copy over, you can directly run it here. So that might be a little easier. Sorry, this takes some time to share the screen. Once you're able to open it, try to open it and run it, because the first time can take a while. It takes like 3 minutes on my laptop because I need to do some compilation. You can just go ahead and try to run it, and after everyone can get it open up, I'm gonna try and we can look at mine together while yours running on your laptop. You can just run a whole notebook for now, because the whole notebook takes like 5 minutes to run.
Which one are we running?
The sensitivity analysis one?
This one?
Yes, sensitivity analysis super minimal RMS, sorry. So I'm gonna try to, let's look at my screen together. So I'm gonna explain things and then I'll give you some time to play with it.
But we run the whole notebook.
Run the whole notebook, because the
no,
whole
it
notebook will take like 5 minutes, and I'm gonna take 5 minutes to explain things. Okay, borrow your everyone's attention. I'm sorry. So I'm gonna talk through the notebooks. First, we're gonna import packages. And then the first part of this notebook is the same as the flux diagram and ROP notebook that you ran yesterday. So it will load the mechanism, and you can look at the red words here that will tell you what you can choose, what you can change, or like this is the conditions that you want to run the simulation at, like temperature, pressure, number of moles, etc., and how long you want to run the simulation for. And because the beginning part is all the same as yesterday, I'm gonna skip through that and to the sensitivity part. So first we'll do transitory sensitivity analysis, because you don't need to solve any equations, so you can just plot it. So here it plots out the sensitivity equation, transitory sensitivity for the rates, and you can experiment with like different tolerances, different time, and see what it will change. And here's the transitory sensitivity of thermal chemistry, and you can try to play with that. And I also show the comments here that what you can change. And after that, it will be an adjoint sensitivity equation. So this function, I try to solve the adjoint sensitivity equations that I showed previously. And then we'll have the same two plotting function that get called. And then after that, we will do the threaded forward sensitivity version. And as you can see, it's kind of follows the same order. It plots out the rate sensitivity, and then it plots out thermal sensitivity. Eventually, the last thing that I let you do, so like the sequence I show is kind of the fastest to the slowest, so that you can look at the fast part first when it is running. And the last step takes the longest time with the traditional forward sensitivity. It will solve that, and you can play with the plotting function. And let's try to do this for like 10 minutes. Is that too long? Is that good? Okay, I'm gonna continue with the slides part. So here I'm gonna talk about some how things are constructed in RMS and what are the things that you see in a code notebook and what it means, like what assumptions that they assume. And then at the end, I will hopefully have some time for you to run the other notebook. So RMS simulates things with a few blocks. So the first block is like it's called phase. It basically describes whether your system is gas phase, liquid phase, or surface. What it does is it controls the how thermal and kinetic parameters are calculated, say like liquid phase, you want to incorporate the diffusion limitation, etc. And yeah, so in our RMS, there are 3 phases that we currently support. Ideal gas and assume ideal gas. It's kind of like self-explaining. Ideal dilute solution assumes dilute solution and it's ideal such that the interaction of species don't get into each other's way, kind of like that, an ideal surface. And the second level of thing is called domain, where there are many options. What it controls is what assumptions are made when you do the simulations. And it often corresponds to your physical system. Like some domain like constant volume, it will correspond to if you do experiments and if your reactor size is not changing during experiment, you will use a constant volume. If your reactor temperature is not changing during experiments, you can use constant temperature. If the pressure is constant, you can do that way too. And the next thing is interface. There are many options. It controls the transport, for example, like inlet and outlet, and like vapor liquid mass transfer, etc. Those kind of things. It also controls the multi-phase reactions, like a reaction happening between a species in a gas phase and a species in a surface on a surface. So there are 2 types of interface in RMS. First is this one, it just interacts with one phases like an inlet or outlet. There are also interface for multi-phase that can connect 2 domain, like if you want to do a vapor liquid, like if you want to do a reactor that have 2 phases, that vapor and liquid, and both phase have reactions happening, you want to use some multi-phase setting. Or if you want to do like a gas phase and surface reaction, you will also have 2 phases, and you will have an interface connecting for the reaction. And the final thing that plays into the RMS simulation block is that we have a object called reactor. It basically handles all the numerical details. It do a lot of optimization under the hood to try to make it solve faster for your system. I won't go into too much details here. But basically, it put in together a domain that you construct previously and give you a reactor object. And you can access the recommended solver using this way. So instead of what we put in right now, which is we use Siebel BDF for all the examples, you can access this one and see, and it will be the recommended solver for your system. Okay, so here are some common uses of different domains. For ideal gas, we have 6 different domains with different use cases. I'm not going to go into details of this because it's quite self-explaining. For system that you know the volume profile, like a rapid compression machine, so you know the volume at each time points, you can give it the volume profile, and it will try to solve the equation exactly at each time points for your volume of the experiments. And liquid phase, we have 2. So this one, it's for a reactor that's like slowly heating, and you can give it a temperature profile and solve it that way. And for the ideal surface, we currently only support 1, but we're still working to improve. There are other interfaces that we support. There are interfaces for single phase inlet, outlet. The upper 2 are for molar flow rate, and then the middle 2 volumetric flow rate are defined using volumetric flow rate. It's quite self-explaining. You want to use volumetric flow rate when you control the system using some sort of flow meter that control the volume flow rate. And for multi-phase, we support the multi-phase reaction or multi-phase mass transfer. And using these combination, it's kind of like Legos. You put things together to, you just combine all these options together to make it to do what your system do. So the example that we ran yesterday, we ran it on ideal gas assumption. We ran it on constant value assumption, and it will solve the system this way. And these are the figures that I believe you all see yesterday. And another interesting example that I did for the paper is we can do a vapor liquid thermal cracking heavy oil to gasoline. So what it does is we take this published mechanism from our group and I apply solvation corrections to it and I model it as an explicit two-phase. So what I want to model is I have a liquid heavy oil and I heat it up to get it thermally cracked. And as it reacts, the lighter species can evaporate into gas phase and get blowing away. So that it will keep cracking into gasoline and blowing away that way. So what I do is I simulate it with ideal gas assumption, constant temperature and pressure, and I give it output called volume maintaining output. It's because the amount that it evaporates from the liquid phase can change. So it's not a constant. And I want to maintain a gas phase as a constant volume. So I give it that. And for liquid part, I use the dilute solution assumption. Sorry. In constant temperature volume assumption, and I use this interface to do the vapor liquid mass transfer. And this way we can plot out like how the mole fraction changes in vapor, how the mole fraction changes in liquid, and the flux diagram works on the multi-phase case too. So for now, we're gonna work on this one together. I borrowed the example generated from RMG catalysis example. The one I share is not a complete version because it's not the newest version. I tried to regenerate it, but I don't have enough time to finish it, so I just copied it from an older version. So what we are going to do is we're going to simulate it as a gas and surface two-domain multi-phase reaction. There's some reaction going on in the gas phase, there's some reaction going on the surface, and there's some reaction going on across the gas phase and the surface. And we're gonna try to plot these three plots. Okay. So if you can go back to the Jupyter notebook, we can open the other notebook that I showed. It's called Simulate Methane Oxygen Catalog. And when I send out an email, I also send out a mechanism file. So you should copy that and put in a folder as well, because running this line can take a while, and I don't think we have enough time right now. You can just copy that mechanism file I sent you. And you can do the same thing, run everything. And I'm gonna talk about notebook after everyone gets this notebook running. Okay, follow everyone's attention.
You have my undivided love.
Thank you. I'm gonna just go through what it's doing. It's basically very similar to the notebook that we ran yesterday on the super minimal example, but this one is multi-phase. So it basically do the same thing. We import packages, we load the mechanism, and it's doing slightly different thing here because now this mechanism contains two-phase information. First, it will try to load the gas phase species and reactions, and then it will load the surface species and reactions. And this part is trying to get the interface reactions from the mechanism file. So here it prints out that we have 12 species in gas phase, 3 reactions in gas phase, 29 surface species, and 200 surface reactions, and 21 cross phase reactions. And you can change the simulation inputs over here. I kind of just put random numbers over here based on the, well, you know, we will learn about how to generate this hopefully tomorrow in tomorrow's lecture on RMG CAD, and you will know more closely how to generate this mechanism. But basically, you can change the temperature, pressure, reacting surface area, site density, all that. And you can learn more about this tomorrow. And we will do the same thing. First, we select the phases. It has ideal gas, ideal surface, and we set out domains which control the assumptions we make. So as I said before, we are using constant temperature and pressure domain. and we're using constant temperature and area domain for surface. And we add one thing for the interface reactions, and we say that reactor, we solve the ODE, do the same thing as before. And we kind of just use the same functions that we used yesterday to analyze the result. Not here, because when you put it into the reactor, we put the first one is gas, the second one is catalysis, which is surface, and Python uses 0 index. So when you put 0 here, oh, sorry, 0 is the other. When you put 0 here, you refer to the first domain, which is the gas phase domain. So you plot the gas phase domain out this way, right? Excluding the nitrogen, because nitrogen doesn't really do anything interesting in this mechanism at least. And here, when you put 1 here, it refers to a surface domain. And you can plot the flux diagram using the same function that we saw yesterday. So you can see here, it kind of quite nicely shows both the gas phase reactions. Well, it shows both the gas phase species and the surface species and the reactions between them. So it shows everything like in one plot. And you can also do our piece on this. Here I try to look at the oxygen atom on the surface, and this is what it shows up. And you can try to change different species, different time points, etc. when you make this plot. And tomorrow we'll learn how to use RMG CAD to generate these mechanisms. And yeah, I think this concludes my presentation today. And feel free to be playing with the notebooks or email me any questions. And I'm also happy to take any questions.